This morning, we're actually going to start with a little bit of section 6.1 that we didn't quite get to last time, which was how to determine what sample size you need for a desired margin of error. So we talked last time about constructing confidence intervals, and sometimes you can construct your confidence interval, you get your margin of error in the end, and maybe it's gigantic. Maybe it's like plus or minus 10 percentage points or something like that. And you might not think that that's very useful. So it would be helpful if you kind of know what you want your margin of error to be in the end, maybe 3 percentage points, 4 percentage points, 5, 1, whatever, to be able to figure out, okay, well then what size sample would I need to collect in order to get that margin of error that I want? So here on the screen, you can see this is the formula that we have for margin of error, the margin of error portion of our confidence interval. And if I want to figure out what sample size I would need for a particular margin of error, I can basically just take this formula here and algebraically solve it for n. So once I do that, so if I manipulate everything around algebraically, then what I end up with is this. And so we can use this formula then, like I said, to figure out what sample size we would need for a particular margin of error. So looking at the parts of this formula, this Z star value, it comes from our level of confidence. And last time we talked about how there's basically 3 levels of confidence that are the most common: 90, 95, and 99%. And based on how confident we want to be, that's the value of Z star that we're going to use here. So this ME that we have here, that's going to be our desired margin of error. So whether that's 3%, 4%, 5%, 1%, we're going to plug that in right here. And we always plug this in decimal form. So if I want my margin of error to be plus or minus 3%, then I would use 0.03 here. All right, and then this P tilde, remember, we're trying to figure out what sample size we need before we've actually collected any data. So P tilde is going to be our best guess for what P is. And sometimes we might have something we could go off of, like maybe a pilot study that had been done, historical data. If you think about things like political polling, those are big these days, right? Then if you're going from week to week, asking basically the same question, like who are you going to vote for in the upcoming election, then those values probably don't change a whole lot week to week. So you could use last week's number in this week's to help you figure out the sample size for this week, kind of thing. So if you have some kind of prior knowledge or information, you can use that as your P tilde. Now, sometimes you might have no idea, like this is the first time you're collecting data on this. You really have no clue what P is. That's why you're collecting the data. You're trying to figure it out. And if you have no idea, then you're going to use P tilde equal to 0.5, which is 50%. The reason why you're going to use this if you have no idea is because this is the P tilde value that will end up giving you the largest sample size. And so if you're using that, it's like the most conservative, like for sure, you're going to get the margin of error you want if you use this sample size kind of thing. So it's nicer if you have something to go off of, because then you can get by with a little bit smaller sample size and still get the same margin of error, assuming your something to go off of is different than 50%. But if you don't know, then we just use the 50% estimate. Make sure when you look at this, it is 50% and not 5%. So because we use an alpha level of 0.05 a lot, then sometimes students get the 5 and the 0 mixed up on this. But for P tilde, the kind of, if you have no idea, use this P tilde value is 0.5, which is 50%. And then we're always going to use everything in decimal form. So that's going to be your margin of error and your P tilde value. And we're always going to round up. So let's look at a couple of examples, and this will totally make sense. So first one, PTC is a substance that has a strong bitter taste for some people and is tasteless for others. The ability to taste PTC is inherited. About 75% of Italians can taste PTC, for example. You want to estimate the proportion of Americans with at least one Italian grandparent who can taste PTC. Starting with the 75% estimate for Italians, how large a sample must you collect in order to estimate the proportion of PTC tasters within plus or minus 4% with 90% confidence? So looking back at my formula here, I can see that I'm going to need to have Z star, which is based on my level of confidence. I'm going to need to know my desired margin of error, and I need to know my P tilde. So I like to write all those things down ahead of time. So we said Z star, which is based on our level of confidence. We also need to know what margin of error we're desiring and our P tilde value. So I look in the problem and I try and figure out all these things, and once you write all those down, it's just a matter of plugging in and solving. So starting with, let's see, we want to be 90% confident. So my confidence level is 90%. Now, who remembers from last time, or if you just have that little chart in front of you, what is Z star for 90% confident? Yeah, there we go. For 90% confident, it's 1.645. So we're going to use 1.645 as our Z star. Okay, next, our desired margin of error. Well, it says we want to be within plus or minus 4%. But remember, we always want to use the decimal form. So I'm going to have 0.04 there. And then P tilde, in this case, it says starting with the 75% estimate. So they're saying, hey, go ahead and use 0.75 as your P tilde. So we'll throw that in there. All right, now we're ready to plug everything into our formula. So N was equal to Z star, which is 1.645, divided by our desired margin of error, so that 0.04, and this whole quantity is going to be squared. So we had Z star over ME squared, and we multiply that by P tilde, which is 0.75, times 1 minus P tilde, so 1 minus 0.75. So now we're just going to work this out on the calculator. So we're going to do everything inside the parentheses here first. We're going to square that, and then we can multiply it by those other things there. So I'm going to start here with those parenthesis values. So if you take the 1.645 divided by 0.04, then you get 41.125. Now I'm going to square that 41.125, and I get 16.91265. So for this first part, I get 1691.2656. Okay, now I'm going to do this second part with the 0.75 times 1 minus 0.75. So 0.75 times 1 minus 0.75 is equal to 0.1875. All right, now I have to just multiply those two things together, and we'll see what we get. So I have 1691.2656 times 0.1875, and I get 317.11. All right, and remember, this is telling us like the minimum sample size that we need in order to get the margin of error that we want. So I need at least 317.1123 people. But of course, when we go to actually collect our sample, it's not possible to collect 0.11 of a person. We can't just sample like their right arm or, you know, their left leg below the kneecap or something like that. Of course, we would take the entire person. So when we are looking at sample size, we always round up. Okay, so we don't use standard rounding rules here. If there's any decimal, any little piece at all on the other side, we're going to round up. So that, in this case, that means that we're going to need 318 people for our sample size. All right, questions so far? All right, let's look at another example here. Suppose you wish to estimate the proportion of ACC students who work full-time and go to school full-time. You have no idea what this proportion might be beforehand. What size sample would you need in order to estimate this proportion within plus or minus 3% with 99% confidence? So again, I like to figure out all my variables first. So I need to know Z star. I need to know my level of confidence. I need to know what I want my margin of error to be. And I need to know my P tilde. So looking at my problem here, says 99% confident. So what Z star goes with 99% confident? Yeah, 2.576. All right, and the easiest way to get the Z-star number is just by looking at that little table that we had, because since there's only like 3 values that we're going to see most of the time, it's nice just to keep those as a handy reference. But of course, if you don't have that handy reference, then you can find this on StatKey by going to the normal distribution, clicking on two-tail, putting whatever your confidence level is in that center box. And then when you do that, the bottom right box will be your Z-star value. But once you've done it once, you kind of don't need to reinvent the wheel every time, as long as you keep that little list handy. All right, so my desired margin of error, it says I want plus or minus 3 percentage points. Of course, I'm going to enter that as a decimal. And P tilde, it doesn't give me anything. It says I have no idea what the proportion might be beforehand. So when I have no idea, then I use 50%, which is 0.50. All right, now I'm ready to plug everything in. So I'm going to have n is equal to 2.576 over 0.03, that whole thing squared, times 0.5 times 1 minus 0.5. So starting here, 2.576 divided by 0.03 gives me 85.866666. Then I'm going to square that, and I get 7373.084. Okay, then I'm going to take 0.5 times 1 minus 0.5. That gives me 0.25. So I end up with 1843.271, but we always round up. So I'm going to end up needing to sample 1,844 people. Okay, so this isn't really too tricky. Let me tell you like the 3 ways that sometimes people make mistakes here. So one way that they make a mistake is by not rounding up. That's pretty common. So always round up when you're doing sample size. Another thing people do that fouls them up is they don't use decimal forms of the number, because a lot of times, like it is in this question, they'll be like, hey, 3 percentage points or 3 points or 3%. And so sometimes people just use the number 3 there instead of 0.03. So everything has to be in decimal form in order for this to work out right. And then the last mistake that gets made fairly frequently is people forget to square this first part here. I think because the little squared sign is cute and little and it's in the upper corner, because I've seen this on paper exams when I'm grading people's work on paper exams, how they'll actually write it in the initial when they write everything out, and then by the time you get to the next step, like it's just disappeared into thin air because it's little, like I said, and it's easy to lose track of. So don't forget the squaring part there. And something that might help with that is if you get a sample size number that seems kind of low, then that might be an indication that you did something wrong along the way, especially with proportions. When you're looking at proportions, you typically need much larger sample sizes than you do when you're measuring a quantitative variable and looking at means. So you should be getting pretty big numbers in general. So if it's telling you you need a sample size of 8 or something, then that's a good indication that you did it wrong. All right, so last time we talked about doing inference for one proportion, and if doing inference for one proportion was fun, what would be even funner? You guessed it, doing inference for 2 proportions. So that's what we talk about here in section 6.3. And you probably noticed that we skipped over section 6.2, but don't worry, we're going to come back to it next week. I think it's a little bit more logical to do like 1 proportion, 2 proportions, and then next week do 1 mean, 2 means, rather than kind of mixing up the means and proportions within the week. So that's why we're doing it that way. One thing that can be really tricky when you're reading through a problem is to figure out if the problem's referring to 1 proportion or 2 proportions. And I think this is especially tricky when we're dealing with proportions because typically when the variable that we're measuring is going to place people into 2 groups. Automatically. So sometimes people think, oh, I must be talking about 2 proportions because I have these 2 answers kind of thing. But the difference between a 1 proportion problem and a 2 proportion problem is the actual number of variables that we are measuring on each individual, on each case. So in a 2 proportion problem, we are measuring 2 separate categorical variables, okay? And each of those categorical variables has 2 levels to it. In a 1 proportion case, we're measuring only 1 categorical variable, but again, that 1 categorical variable is going to have 2 levels, which is what throws things off a little. So we're going to look at some practice problems here and see if we can guess the right thing. So, and I'm going to pull up my poll window so you can place your guess in the poll. So here's the first one. Suppose you want to compare the proportion of students who use a Windows-based PC to the proportion who use a Mac. So does this look like inference for 1 proportion or inference for 2 proportions? All right, most people voted for B, but B is actually incorrect. This one is a 1 proportion problem. See, I told you these were a little bit tricky, right? So this is a 1 proportion problem because we really only measured 1 variable. We asked the students, hey, what type of computer do you use? You know, do you use a Windows computer or do you use a Mac? So that's just 1 variable that we measured. Therefore, we're dealing with just 1 proportion. All right, let's try another one. This time, you want to compare the proportion of students who study abroad between those attending public universities and those at private universities. So does this look like inference for 1 proportion or inference for 2 proportions? All right, the majority of the people chose B this time, and B is the correct answer. So this time we're looking at 2 proportions because we measured 2 variables on each of the individuals. So one variable was whether or not they studied abroad, and the other variable was whether or not they attended a public university or a private university. So there's 2 variables there that we measured, making it 2 proportions. Okay, here's another one. This time, we want to compare the proportion of in-state students at a university to the proportion from outside the state. So is this 1 proportion or 2 proportions? All right, good job. The majority of the people chose A, so I think you guys are starting to get the hang of this. It's inference for 1 proportion because we really only measured 1 variable, like in-state or out-of-state. Okay, that was the 1 variable that we looked at, like you could call it location or something. All right, and another one here. This time you want to compare the proportion of in-state students who get financial aid to the proportion of out-of-state students who get financial aid. All right, majority of the students chose B, and B is the correct answer. So this time we measured 2 variables on each person. We measured whether they were in-state or out-of-state, and we measured whether they got financial aid or did not get financial aid. So we have 2 variables, therefore we're dealing with 2 proportions. All right, so this next part, you don't need to write anything down yet. I'll tell you when you can start writing stuff down. This is just kind of the background, like building up to the part I want you to write down. But we will be looking at inference for the difference in these 2 population proportions. And in order to do that, we're going to have to look at the sampling distribution for the difference in the 2 sample proportions. And the formula for the standard error for the difference in those 2 sample proportions is this big thing right here. And when you look at this, you notice we talked last time about how we couldn't use the standard error formula directly in a 1 proportion case because it involved parameters, and same thing this time. So we've got this P1, P2 in this formula, and in real life, we don't know P1 and P2, so we're going to have to do something about that. We're going to have to approximate those values. However, we do know that the distribution of p hat 1 minus p hat 2 is approximately normally distributed. The mean is equal to the parameter value, so the actual difference between p1 and p2. And then, of course, this is the same standard error formula that we looked at before. So this just means that we are going to be able to use that normal approximation as long as our sample size is large enough. And now we're dealing with 2 samples, which means we have like 2 sample sizes, 2 sample proportions. So everything gets just a little bit more complicated. It's just like when you have your second kid, like it's not twice as complicated, but it definitely does like increase the chaos level at your house a little bit. So we're gonna increase the difficulty just a little bit because we have more things to keep track of. And again, you notice that all of these things involve P1 and P2, which we don't know. So when we actually talk about the confidence intervals and hypothesis tests, we'll tell you what to fill in for those values. So first, let's talk about confidence intervals this time. So we said, okay, here's the standard error formula, which we can't use as is, but when we're doing a confidence interval, then our best guess for P1 and P2 are going to be P hat 1 and P hat 2. So we're going to go ahead and substitute P hat 1 and P hat 2 into this formula. Okay, so this is the part where you can start writing this down on your notes. So our general format for this confidence interval is going to be p hat 1 minus p hat 2 plus and minus z star times the standard error. And the standard error is going to be that really fun formula with p hat 1 and p hat 2 rather than p1 and p2. So it looks like this. And the conditions that have to be met in order to make sure that our sampling distribution for p hat 1 minus p hat 2 is normal is that we need n1 times p hat 1, n1 times 1 minus p hat 1, n2 times p hat 2, and n2 times 1 minus p hat 2 to all be greater than or equal to 10. Now, because we're using all p hat values here, another way to look at these is n1 times p hat 1 is really the same as the number of successes in sample 1. Or in group 1, I'll say. So it's the number of successes in group 1. And n1 times 1 minus p hat 1 ends up being the number of failures in group 1. Remember, successes is just the count of whatever it is that we're interested in, whatever that happens to be. So this is number of failures in group 1. And then similarly for group 2, n2 times p hat 2 is really just the number of successes in group 2. And n2 times 1 minus p hat 2 is really just the number of failures in group 2. So depending on how the data is presented to you, making these calculations or just looking at the number of successes and failures, one of those might be an easier option for checking the conditions. So we'll look at some of that as we go through our examples here. All right, so our first example is dealing with metal tags and penguins. We want to know how detrimental are metal tags to penguins. A study looked at the 10-year survival rate of penguins tagged either with a metal tag or an electronic tag. 33 of the 167 metal tagged penguins survived, compared to 68 of the 189 electronic tagged penguins. So our goal is going to be to give a 90% confidence interval for the difference in proportions. Before we get to actually constructing the confidence interval, though, we have to set everything up. So first, we're going to define our parameters. And in this case, because this is a 2 proportion problem, then we're going to have 2 proportions that we have to define. So we could have P1 and P2. You could also call them PM and PE for metal and electronic. That's what I'm going to call them. So PM would be the proportion of surviving metal-tagged penguins. So proportion of surviving metal-tagged penguins. And similarly, PE is going to be the proportion of surviving electronic tagged penguins. So PE is proportion of surviving electronic tagged penguins. All right, so now we've defined our parameters. We're ready to start thinking a little bit more about our confidence interval. So first we're going to compute our sample statistic. So if we're looking at PM and PE, our sample statistic is going to be P hat M minus P hat E. And remember that little chart that we used last in chapter 4 to kind of help us figure out what our hypotheses were, what the sample statistic was, and all that. That same chart is still pretty useful in this chapter as well. So I know that if I'm looking at 2 categorical variables, then I have to define P1 and P2, and I know that my sample statistic is P hat 1 minus P hat 2. So before I can figure out what this quantity is, though, I first need to figure out what P hat M and P hat E are equal to. So for the metal tagged penguins, it says 33 of the 167 metal tagged penguins survived. So that's going to be 33 out of 167. So if I do that calculation, 33 divided by 167, then I get 0.198. So I get 0.1976, so that would round to 0.198. And then P hat E, for the electronic tags, it says that there was 68 out of the 189 electronic tagged penguins. So that's going to be 68 out of 189. So 68 divided by 189 gives me 0.3597, so that would round to 0.360 if I'm doing 3 decimal places. You always want to do at least 3, and oftentimes I'll do 4 or more out here. And then when you're doing any intermediate calculations, then you definitely want to do as many as you can, or keep as many decimal places as you can as you're going through. Okay, so now I have my P hat M and my P hat E, so I can subtract those. So I'm going to get 0.198 minus 0.360. 0.198 minus 0.360 gives me negative 0.162. So negative 0.162. So this is the value of my sample statistic right here. And then, of course, the correct notation is this part here, the P hat M minus P hat E. All right, so I've defined my parameters. I've got my sample statistic. I'm almost ready to start computing that confidence interval. But first, I want to check my conditions and make sure that they meet the conditions in order to use the normal approximation, in order to use that formula and stat key and everything to construct our confidence interval. So remember our conditions. We had N1 times P hat 1, N1 times 1 minus P hat 1, N2 times P hat 2, and N2 times 1 minus P hat 2. We need to figure out all 4 of these quantities, and then we need to make sure that they're all at least 10. So the first one, N1 was 167, and P hat 1 was 0.198. So if I multiply 167 times 0.198, then I get 33. Okay, so notice this is the same as the number of successes that we had up there. Down here, if I take N1, which is 167, times 1 minus 0.198, I get 134. Okay, this is also equal to the number of failures. So another way that you could get this same number is if I take my N and I subtract my number of successes, so 167 minus 33, that should be equal to the number of failures, which is this number right here. So there's kind of two ways to get at the same number. Whichever way you like best will work just fine. Okay, so the second one here, N2 times P hat 2, that's going to be the same as the number of successes in my second group here. So I'm just going to put the 68. And for my number of failures, the N2 times 1 minus P hat 2, this time I'll do it the subtraction method. So I'll take 189 minus 68, which is 121. All right, so now I have to look at all four of these numbers and see if they're greater than or equal to 10. And they're all greater than or equal to 10. So yes, we meet the requirements. So I'm going to say yes, all successes. That says successes. It's really hard to write on a computer. All successes and failures are greater than or equal to 10. All right. This is kind of tedious. It is kind of a pain and it's a lot of work, but on your homework and things, and on the exam, I'm going to want you to show me all this stuff, okay? If there's a question that says, are the conditions met, and you just tell me yes or no, you're going to get no credit for that, okay? You have to show me how the conditions are met. So I want to see all of these numbers, okay? You need to say, look, I have 33 that's greater than or equal to 10, 134, 68, 121. I need to see all those numbers. Whether you get them via using this equation or whether you compute the successes and failures the way we did on the bottom half here is fine, but I need to know that you knew what you were actually talking about and that you weren't just guessing when you told me that you met the conditions. All right, so for our confidence interval, this time we wanted a 90% confidence interval. So what's the Z star value that we're going to use for 90% confident? Yeah, Z star for 90% confident is 1.645. So we're going to use 1.645 for our Z star. All right, so now we're ready to actually construct this confidence interval. So here is our formula for the confidence interval, and we're just going to take all of our numbers and plug them in. And I didn't put my n's up there. I think the first n was 167, so that was n1, and n2 was 189. Okay, so now I have all the numbers I need. I plug them all into this formula here. And we're going to see if we can work this out. So I'm going to get 0.198 minus 0.36 plus and minus 1.645 times the square root of this whole big thing, 0.198 times 1 minus 0.198 over 167 plus 0.36 times 1 minus 0.36 over 189. All right, so start by doing this piece by piece. So we can take the 0.198 minus 0.36. This is going to be the same as our sample statistic that we already calculated. So we should get negative 0.162. All right, and then we're going to work on calculating this big old thing over here, which is our standard error. So I usually do like this piece first, and then I do the second piece, then I add them together, then I square root it. So starting with this first piece here. So you can work on it on yours too, and I'll put the intermediate calculations up as I go along so you can check your answer as you go along if you want to, and we'll see if we arrive at the same answer. All right, so I've got some intermediate calculations here. Now I'm going to add those two numbers together. Notice how I use tons of decimal places for my intermediate calculations. And I'm only going to round when I get down to the last part where I'm looking at the margin of error and constructing the confidence interval. All right, so I added these two numbers together. I took the square root, and that gave me a standard error equal to 0.0466 or 4658. All right, or on my presentation, I guess I rounded it to 0.047. All right, so now I can multiply those together to get my margin of error, the part on the right side here. So once I multiply 1.645 by that standard error, and I used the long number in my calculator to multiply, I ended up with a margin of error of 0.0766, which I guess would round to 0.077 if I'm doing 3 decimal places for my final answer. All right, after all that work, then now we're just ready to construct the confidence interval. So I would take negative 0.162 minus 0.077, which gives me that negative 0.239. And then I'm going to take negative 0.162 plus 0.077, and that gives me that negative 0.085. So finally, we get our confidence interval out of that whole thing. All right, so how many of you made it to this far and you actually got the right answer? So give me a smiley face in the chat window if you were able to get all these calculations and get down to this answer, or give me a frowny face if you something went wrong in the middle and you never made it this far. All right, good. Lots of smiley faces. That's excellent. Or maybe the people that would put frowny face are too afraid to put the frowny face in the window. All right, so this is, as you can see, it can get really tedious to do all these calculations, and there's a lot of room for error in doing these calculations. So I'm going to show you something else that is going to change your life, and I think you're going to like it. And basically what it is there's a website that will find the standard error for you. So it's like a standard error calculator, standard error applet. Sometimes I call it an applet, sometimes I call it a calculator. So how would you like it if this whole part over here, everything under the square root sign and including the square root sign, was done for you, and you just got this magical standard error number out of it, and then you could just keep computing with that value? That would be pretty awesome, right? All right, so let me show you how to do that. And you are going to be allowed to use that on your Wiley Plus homework, and on the exams, then I'm actually going to give you the standard error number for these two proportion problems already done for you. So it kind of saves you the worst part of the calculations, which is pretty handy. So let me show you where to find that. So here's our class in Blackboard, and there's a couple of different places that you can find this in Blackboard. So first of all, if you go to course links, this just has a bunch of stuff that's helpful for our class. This is where the tutoring information is, homework answer keys, link to Wiley Plus, link to StatKey, and down here we have the SE calculator. So this is the one that you're going to click on. Notice also down here there's tables. Well, this shows tables and formulas. So this one has our formula sheet, the chapter 6 formula sheet. Let's see if I can make it come up on here. There we go. So you might want to print out this formula sheet and keep it handy while we're going through chapter 6, because there's kind of a lot of formulas here. And in fact, there's so many formulas that test 4 is the only exam that I am going to allow you to have a formula sheet on the exam. So in addition to your one page of handwritten notes, you may also have the formula sheet printed out to have handy on the exam as well. Notice though that all the formulas on here, they are the full-on formula. So if I give you the standard error, you have to know where to plug that standard error in. So you need to know which part of the formula is the standard error. Okay, so let's go back and show you how to use that standard error calculator next. Okay, and I was also going to show you that it's in the week 11 folder for this week too, and I'm going to put it in the week 12 folder also. So down here where it says week 11 resources, this is just the week 11 folder, like where you get your homework from. Then it has a direct link here, standard error calculator, the formula sheet. We're not going to really use table A in our class. We will be using this critical values for confidence interval table, but you're not going to need it a whole lot in this week, but you will need it for next week. Okay, so I'm going to click on this SE calculator. Once I get into here, I'm looking for the standard error for difference of sample proportions here. So I'm going to click here where it says SE sample proportions, and it's going to ask me for my data. So for my penguin data in the metal tagged group, there was 33 that survived out of 167. And in the electronic tagged group, then I think there was 68 out of 189 that survived. All right, then you have to tell it whether you're doing a confidence interval or a hypothesis test. So we're doing a confidence interval, and then you click on compute standard error, and look how much faster that was than plugging all those numbers into your calculator. That was pretty fantastic, right? All right, so this is the number that I would get for my standard error, 0.04656. And if I look back here, that was pretty much the same number that I got here. The calculator actually doesn't round your p hat and p hat 1 and p hat 2 numbers. So that's why my number that I got is just slightly different, because I rounded my 0.198 and my 0.36 numbers, but that one did not round. So then I could just take that number that they gave me here, the 0.04656. I know that that number is going to replace the square root and everything underneath it to be my standard error. So then to compute my confidence interval, all I would have to do is multiply that 1.645 times the standard error number that's already been calculated for me, and then add and subtract that to come up with my confidence interval. So that looks like a lot more fun than doing the nasty formula, right? Unless you were like really excited because this is the week where we finally start doing lots of real math. And this whole semester, you've probably been like, man, where's the math in my math class? And then you got to this chapter and you're like, yes, formulas, I love them. How many things can I plug in? Make it more complex. But if you were not saying that, then you'll like the standard error calculator. Okay, so however you get your confidence interval, whether you plug all the numbers into the formula or whether you end up using the standard error calculator, you should get the same confidence interval out. And now we can interpret that confidence interval. So we would say we are 90% confident that the survival rate is between 0.1085 and 0.239 lower for metal tagged penguins as opposed to the electronically tagged penguins. There's different ways to write the conclusion. If you want to keep it like the very standard way that we've been writing it, where we say we're 90% confident that the difference in the proportion of surviving penguins for metal tag versus electronic tag is between negative, 0.239 and negative 0.085, then you can totally do that. The negative part is taken into account in the way I wrote it here with this word lower. So this way uses a few less words and means the same thing. But if you're worried about messing up how you write it, you can stick with our traditional method. All right, so next let's look at a hypothesis test for difference in proportions. So first of all, when we're writing our hypotheses for two proportions, the null hypothesis is always going to be that P1 is equal to P2. And then the alternative hypothesis is going to be that P1 is either greater than, less than, or not equal to P2. Okay, and which symbol you choose is going to depend on the wording of the question, what it is that you're trying to find out. So this, the way that we write the hypotheses, same way we were doing it in chapter 4. When we're doing a hypothesis test, remember, we're always trying to figure out the p-value, which is computed assuming the null hypothesis is true. So if the null hypothesis is true, then that means that P1 is equal to P2. So thinking about our standard error formula, and again, it has that problem, has the P1s and the P2s in it. When we did a confidence interval, we replaced these with P hat 1 and P hat 2. But when we're doing a hypothesis test, we're starting with that assumption that the null hypothesis is true. And if the null hypothesis is true, then we could actually combine all of the data into one big group if P1 and P2 are actually the same. So for example, let's say we were looking at men and women and their favorite color of M&M, okay? And if we do a study and we find out that 30% of men prefer green M&Ms and 30% of women prefer green M&Ms, then we don't really need to walk around telling everybody, hey, 30% of men and 30% of women prefer green M&Ms. Instead, we could just put everybody together and be like, hey, 30% of all people prefer green M&Ms, right? It doesn't make sense to keep talking about them as separate groups if they're really the same. So keeping on that idea, if the null hypothesis is true, then we could use the same number for both of these. And the number that we would want to use is what we call a pooled proportion. Okay, so essentially we would combine all the data together as if it came from one big sample rather than two separate samples. So to find our pooled proportion, this pooled proportion P hat, we're going to take the number of successes in both samples combined. So number of successes in both samples divided by the total number of observations in both samples. So we can add the sample sizes together. So we're basically going to add the successes together for the numerator, add the sample sizes together for the denominator, and then divide those. And that's going to be we're just going to call it P hat because now it's just representing one group, and we're going to call it our pooled proportion. And so then when we're figuring out our test statistic, then we're going to use that pooled proportion in place of P1 and P2 in our standard error formula. And when we do that, and it kind of simplifies down, this is what the resulting formula looks like. So this is our test statistic. It's a Z test statistic. And we're going to have P hat 1 minus P hat 2 divided by square root of P hat, which is the pooled proportion. I'll write that under here, where P hat equals pooled proportion. And somewhere around this formula, you might want to write out how we get the pooled proportion. So taking the number of successes in both samples combined divided by the number of observations in both samples combined. All right, and we're going to find that this whole part down here in the denominator, this part is our standard error. And we can actually use that standard error calculator to help us figure out the standard error on this one too. So when you use the standard error calculator, then your Z is just going to be equal to P hat 1 minus P hat 2 divided by the standard error. Look how much simpler it becomes when somebody's doing the dirty work of calculating that standard error for us. Okay, the conditions for the normal approximation are the same as they were for the confidence interval. So N1 times P hat 1, N1 times 1 minus P hat 1, N2 times P hat 2, N2 times 1 minus P hat 2, all greater than or equal to 10. So this is kind of important because remember when we talked about one proportion, the conditions were different depending on if we were doing a confidence interval or a hypothesis test. But when we're comparing two proportions, the conditions are the same. So I'm going to put same as confidence interval. All right, so we're going to look at an example, and before I show you the data, I'm going to show you this little video clip that will help the data make a little bit more sense.
Your jackpot for today is £40,015. The question is now, can you keep it? It's time to play split or steal. Give me your hands, this is great. Come on. You have one final decision to make. You have two golden balls in front of you. They're not cash balls, they're not killer balls. You each have a golden ball with the word split written inside. You each have a golden ball with the word steal written inside. I will ask you in a moment to choose either the split or the steal. If you both choose the split ball, you will split today's jackpot of £40,015 and you will go home, each of you, with £20,007.50. If one of you chooses split and the other one chooses steal, whoever chooses the split ball goes home with nothing. But whoever chooses the steal ball goes home with the whole £40,015. Here's the rub. If you both choose the steal ball, you both go home with nothing. Right, I want you to look at your two golden balls to see which is the split ball and which is the steal. Very important you remember what they are. You're happy you know which is the split and which is the steal balls? Are you sure?
Yeah, I'm happy.
Before I ask you to choose split or steal, I'm just going to give you a little time to talk to each other. It's been a very, very eventful day, and you probably have a few things you want to say.
We have come such a long way together. I've brought you through, you brought me through, so we're both equals. 20,000, which is half, is more than I thought I would go away with today. So I am more than happy to split with you if I can trust you to do the same with me. I guaranteed you, I can shake on it now, I guaranteed you at the beginning of the game, if you took me through that round, I would split, and I still intend to split with you.
What I'm going to say to you is, I had my cards read, and I was told if I play fair, I will come away with a substantial amount of money. I'm going to look into your eyes when we're asked to make the decision, and I'm going to be truthfully honest with you. If I look into your eyes and I see that you're genuine and you're going to split that money with me, I promise you, I will make the same decision with you. Can't be more straightforward and honest than that.
I'm going to ask you to choose a split or a steal ball now.
I've made my decision, I'm choosing this ball.
Are you ready?
Yeah.
Steve, Tracy.
All right, so moment of decision. What would you guys choose? So would you split or steal? You can put your answer in the chat window. Put split or steal or S. Lots of splits. There's a steal, couple steals. All right, so thinking about what you would do, we'll go back and watch and we'll see what they ended up doing.
Split or steal? Oh. Steve, you have just stolen £40,015. I have to congratulate you.
Thank you.
Tracy, you've just lost £20,007.50.
Oh well, I came with nothing.
How do you feel?
Gutted. I really trusted you.
So there you have it, the end of another beautiful friendship. So I'll just say they have been very entertaining. I've been Jasper Carrott, this has been Golden Balls. Until next time, goodbye.
When Tracy revealed the split ball, I can't really explain how I felt. I was just so over the moon.
Having lost over £20,000, I was speechless. I don't even know how to put it into words. It's a life-changing amount of money that I just had in my hands and lost within seconds of getting it.
At the end of the day, if you can bluff your way to £40,000, you deserve that money.
All right, I know. I don't think I could live with myself if I sat there and lied to somebody and then tried to steal. So this gives me like anxiety every time I watch that video. All right, so back to analyzing our data though. They did a study in England where they asked people what they would do. Would they split or steal? And they broke down the data by males and females. And we want to find out, are males or females more cooperative? Like, who is more willing to split? So first thing we're going to do is define our parameters. And again, we're doing two proportions, so we're going to have two parameters. So we're going to have PM, which is the proportion of males who would split, and PF, which would be our proportion of females who would split. So once we get our parameters defined, then the next step is going to be to write our hypotheses. So writing our hypotheses, the null hypothesis always has what sign in it? Always has the equal sign, exactly. So we're going to have, whoops. I thought I had it written there. I don't really. Okay, so the null hypothesis is going to be PM equal to PF. And in this case, for my alternative hypothesis, what should be the symbol that I would use? Do I want to use greater than, less than, or not equal to? Yeah, if I look at my question, I just want to know whether males or females are more cooperative. So I'm not indicating a direction at all in my question, either one. I want to know either way. So I'm going to use not equals to in my alternative here. So null hypothesis, PM equals PF, alternative hypothesis, PM not equal to PF. The sample statistic is going to be P hat M minus P hat F. And before we can compute that, then we need to figure out individually what P hat M and P hat F are. So let's start with P hat M. So P hat M is the proportion of males in our sample who would split. So what number should I use in the denominator to figure out this proportion? This time they gave me the data in this two-way table. So it kind of brings back memories from chapter 2 when we first learned about two-way tables. So another way to think about this, remember this is the proportion of males in our sample who would split. So yeah, so we're going to use the total number of males in our denominator, which is that 269. And one thing that you might find helpful is if you use subscripts that kind of go along with the groups, like here male and the other one female, then whatever you use for your subscript, that total is going to be your denominator. So this is males, so I'm going to use the total for males as my denominator. And then for the numerator, of course, I'm going to use the number of splitting males. So 140 over 269. So that ends up being, so 140 divided by 269, I get 0.520. All right, then I'm going to figure out P hat F the same way. This time looking at the proportion of females in my sample who would split. So the total for females is 305, and the numerator would be the splitting females, which is 163. So I'm going to have 163 divided by 305, which is 0.534. So then I can figure out my sample statistic by taking 0.520 minus 0.534, and I get negative 0.014. All right, so this is the value of my sample statistic. So now I'm ready to start thinking about that hypothesis test as soon as I check my conditions. So remember the conditions has that huge long list. So N1 times P hat 1. So in this case, that would be NM times P hat M, and NM times 1 minus P hat M, and NF times 1 minus P hat F. I'm going a little bit out of order, sorry. So NF times P hat F. I've got all four things there. And if they give you your data in a two-way table, the easiest thing to do is just look at the middle four numbers on the table. So anything that's not in a totals column or row are the four numbers that you need to check the conditions. So this is for the males. This is going to be my successes for the males and the failures for the males. And for the females, the 163 is the successes for the females, and the 142 is my failures. So I really don't even have to do the calculations if they give me a two-way table. I can just say, hey, 140 is greater than or equal to 10, 129 is greater than or equal to 10, 163, 142. These numbers are all greater than or equal to 10. So now I'm ready to compute my test statistic. So there's my hypotheses. I've got my sample proportion. Here's my formula for the test statistic. We are going to end up using that standard error calculator to calculate the standard error, which is the whole denominator here. But I do want you to know how to calculate a pooled proportion. So let's talk about how we'd calculate the pooled proportion for this one. So the pooled proportion, remember, is the number of successes in both samples combined. And basically what we're doing, if I can, here we go, if I go back here, see how I calculated my p hat m and my p hat f? To calculate the pooled proportion, I'm essentially taking the numerators from both of those, adding those together, and then I'm taking the denominators from each of those and adding those together. So that's where these numbers are coming from here. So I had, for the males, there was 140 successes. For the females, there was 163. So that's going to go in my numerator. And then in the denominator, there was 269 total males plus 305 total females. So I do the addition first, and then I divide. So I get 140 plus 163, which is 303. And I'm going to divide that by 269 plus 305, which is 574. So 303 divided by 574 is equal to 0.528. So 0.528 is my pooled proportion. And notice that your pooled proportion is always going to be somewhere in between P1 hat and P2 hat all the time. Okay, so if I was going to do this formula over here, that's the number that I would use in place of P hat here. I would use that pooled proportion. But we can also use that fun standard error calculator. So that's what I'm going to go back to here. Let me find it on where I have it open. Here we go. Okay, so again, I click on the standard error calculator, then I'm going to click on SE for sample proportions. I'm going to put in my group 1 for the males, so that was 140 and 269. For the females, I had 163 and 305. So again, these are just the numbers. You guys should be pretty used to these numbers by now, because these are the numbers that you would enter in on StatKey when we were doing stuff with two proportions, and it's the numbers that we use when we divide to figure out our p hat 1 and p hat 2. This time we're doing a hypothesis test. You saw how those formulas were different for confidence interval versus hypothesis test, so it is important that you choose the right one. And then I just click that standard error button, and it tells me that my standard error is 0.04176. So that's the number I'm going to use when I'm figuring out my test statistic. Notice that it gives you a couple of other interesting things here too. It tells you p hat 1, it tells you p hat 2, and it tells you the difference in those sample proportions as well. So back to my problem here. Oh, there's my p hat. So that whole standard error portion, everything down there in the denominator ends up being that just what we found on the standard error calculator. So if you use the standard error calculator, you can essentially skip all this part and just plug in the denominator here, that 0.04176. And then your numerator is your sample statistic, the negative 0.014. So that's going to give you a test statistic of negative 0.335. So again, this is what we call our test statistic. And the test statistic is really just kind of like the middleman that helps us to find our p-value. So to find our p-value, we're going to go to StatKey. So I'll come over here to StatKey. In StatKey, I'm looking at a normal theoretical distribution. So I'm going to click on that here. And my test statistic was negative 0.335, and I had a double-sided alternative. Here, I'll show that back up again before I do this here. So the two things you really need to get the p-value are you need the test statistic, and you need to know if you had a one-sided or what type of test you had, greater than, less than, or not equal to. Mine was not equals to. Okay, so back to StatKey then here. Because it was a two-sided test, not equals, then I'm going to click on two-tail. I'm going to enter in my test statistic on the left side if it was negative, and on the right side if it was positive. So mine was negative 0.335. So I'm going to enter it in on the left bottom box here. So I put in negative 0.335. And then for a two-sided test, I double one of the tail proportions, or I add the two tail proportions together. So twice 0.369, 2 times 0.369 will be equal to my p-value. So I have a little picture of that here. So my p-value is going to be 2 times 0.369, or in other words, 0.738. So 0.738, is that a high or a low p-value? What do you think, high or low? High, right? Like super high. And when p is high, then we keep the guy, meaning we're going to fail to reject. So our conclusion, we fail to reject the null hypothesis. We do not have sufficient evidence of a difference in the proportion of males and females who would split.